So yeah, let's restart again. So I was saying that this talk is about how to aggregate proofs in the resource machine. This is the outline of the talk. First, I will go through some motivation and context. Then I will explain how we can actually aggregate proofs in the Anoma Resource Machine, and then discuss some open questions and next steps. So yeah, we have transactions in the resource machine, which they represent an update of the state. And basically, transactions, what they are is a bunch of resources that can be either consumed or created. They are grouped together. All these resources are grouped together in transactions in different scopes. So we have compliance units. We also have actions, and at the end we have the entire transaction. And this the in the transactions, we have two different types of predicates of relations that we generate proofs for. The first one are compliance constraints or predicates. So this basically makes sure that the resources are compliant with the resource machine rules. And then we have logic predicates, which dictates how the resources can be consumed or created. Basically, they are application-specific constraints. Um, This means that in the transaction, we have many proofs. So we have as many proofs as compliance units and actions, and resources in that are in the transaction. So we have a large size because proofs are large, and also the verification cost for the transaction is high because we have too many proofs. So this is where proof aggregation comes handy in this context. By proof aggregation, what we mean is basically a process in which we have some, let's say, n base proofs. We process them in some way and then output an aggregation proof. This aggregation proof, it needs to be complete. So if the base proofs are valid, then so is the aggregation proof. And most importantly, it needs to be sound. It basically says that the aggregation proof attests to the validity of the input proofs. For our purposes, in order for this to be useful, the aggregation proof also needs to be short and fast to verify. So in particular, we cannot set the aggregation proof to be the composition of all the base proofs because the size is the same and the time to verify is the same as well. We want to do it shorter and faster. This is something that has been in the literature. So, for example, we know how to aggregate gross 16 proofs, exploiting the nature of the verifier that uses pairings. We also know how to aggregate proofs for the Plonk scheme. There are also approaches to use folding schemes for the gross 16 verifier, and there are also aggregation for the Stark proof system, which is the underlying um, scheme that the RISC-0 virtual machine uses. Regarding compliance and logic predicates, since in the Anoma Resource Machine we are using CKVMs, I want to quickly explain how we see them in CKVMs. So basically, these are constraints between the public data that is in the transaction and private data that is either known by users or the prover. And in CKVMs, these constraints or relations are seen as programs where whatever is private is passed as input to the program, and whatever is public is the output of this program. So in this perspective, in the CKVM perspective, what we are saying essentially is that any type of predicates, compliance and logic predicates in our case, are statements for the same relation, which is the universal relation, the CKVM relation. And more importantly, verifying keys is not what we usually understand as the keys to verify a specific circuit. Verifying keys in CKVMs are just the description of the program, or maybe possibly could be as well a succinct description like the hash of the opcodes that constitute the program. Okay. So now that we know more or less how compliance and logic predicates are modeled in CKVMs, let's go through how we can aggregate proofs in the resource machine. The basic recipe is this one. We start writing a CKVM verifier as a program in the virtual machine, and then we use it as a building block to construct the aggregation program. The first step, the CKVM verifier, we give it as granted. Usually this is part of the code of the CKVM that you might use in your project. So what I'm going to discuss now is two different strategies to use this CKVM verification in aggregation. Okay, so for our goal, transactions are just a bunch of compliance outputs and logic outputs, as well as the description of their program. So in this case, the compliance verification key and the logic verification key, and of course the proofs. The compliance program or the compliance verifying key is not part of the transaction because these constraints are fixed and common for all the transactions. So in particular, the compliance verification key as of now is hard coded in the source code, but the logic verifying keys are part of the transaction. Okay, so for the first approach, what that we call batch aggregation, this is the most natural approach. The idea is simple: just take all the proofs that are in the transaction, verify them in one shot, and then if they are valid, then we will output something. So what is this something? This something is consists of, again, all the compliance and logic outputs and the verifying keys. There is a thing here, and is that transactions can have a different number of proofs in them. You might think that the description of the aggregation program varies, is different depending on the number of proofs that appear in the transaction. But this is not the case. This would be the case if we see the aggregation program as a circuit, so like the entire computational trace. But in the CKVMs, we just see them as the program description, and it's actually the computational trace what is generated during the run. But the program itself is just the set of opcodes that describe this aggregation, and this aggregation, it can loop over different numbers of inputs. So the aggregation key is fixed, and we can just hard code it input. Then once we run the aggregation program, we generate the computational trace, and this can be passed to the CKVM prover, who generates a proof attesting to the validity of this computational trace. So this proof is basically the aggregation proof. That attests to the validity of the three inputs proofs. And because we have passed as input the base proof, the compliance and logic proofs, they are not needed for verification anymore to verify the aggregation proof, so they can be removed from the transaction. So once we generate the aggregation proof and it's valid, then we can remove all the base proofs from the transaction. This already saves space in the transaction. And to verify the proofs, of course, the verifier is going to go and grab the verification key that is hard-coded in the code, or in any other place that he trusts. The other approach is the sequential approach. So this follows an IBC-based strategy, incrementally verifiable computation. The idea now is to verify one proof at a time, and to keep track of what has been verified in the past. What we do is we has the outputs and the program's descriptions that have been verified. So we has the compliance outputs, the logic outputs, and as well as the verifying keys for these programs. So in a bit more of detail, the idea is to, in a single step of the sequential aggregation, is to verify the input proof. This would be the incremental step. Then we verify that the previous run of the aggregation is valid as well. So for this step, we would need to pass to the a sequential aggregation program its own verifying key. How this is implemented in practice, what we do is we just pass like an arbitrary verifying key, which purportedly is the verifying key of the aggregation program. And then the verifier, since this key can be hard coded or is fixed, it will use this proof, this verifying key, as the one at the moment of verification. And then of course the outputs of the at each step is going to be the hashes of what has been verified, the compliance and logic outputs and the verifying keys. So maybe this is a little bit confusing. I'm going to illustrate it step by step. So the idea would be to first we start doing the initial execution of the sequential aggregation program. So we would verify that the compliance proof is valid. So imagine, have in mind that in our example, we had three proofs in the transaction: one compliance proof and two logic proofs. So in the first step, we verify the compliance proof, and then we would output the program outputs the hash of the compliance output and of the compliance verifying key, as well as the aggregation as the key that has been used to verify the recursive step, which is supposedly the verifying key for the sequential program. Then once we have run this program, generate a computational trace, and this can be passed to the prover, who generates a proof for the validity of this computational trace. And as output, it gives us an aggregation proof, the first aggregation proof. This first aggregation proof, can then be fed into the next iteration of the sequential aggregation, which will verify this aggregation proof will be used in the recursive step, and as well the incremental step would verify the first logic proof. We keep doing this for the second. Well, we now run the second. We generate the second aggregation proof, and then we feed it again to the sequential program to verify the second logic proof, and generate the final aggregation proof. That finally, this proof attests to the validity of the three inputs proofs for the three proofs of the transaction. Okay. Now the situation is a little bit different from the batch approach. So the verifier, he needs to derive the aggregation instance. So in this case, needs to hash all the compliance outputs and verifying keys to derive the two hashes. And then it goes to the code, it grabs the verifying key, the aggregation verifying key, and verifies the aggregation proof. So this would be the ABC-based approach, the sequential approach. To compare the two approaches, in the batch approach, the prover cost, of course, is amortized among all the transaction proofs. This is because we generate a single computational trace, and on it we generate the proof. But for the sequential approach, we generate as many proofs as base proofs the transaction has. So this is linear, which is not great. In terms of space efficiency, the batch approach depends on the implementation of the CKVM. So in CKVMs, there is this concept of continuations, in which for large computational traces, what you do is you split them into pieces, and then you prove each piece independently. So it doesn't matter how large the computational trace is, you can always run proofs on it. For the sequential approach, we can run it in any CKVM, even without continuations, because it's space efficient by design. And the other thing that I think is important to highlight the difference between these two approaches is the aggregation scope. So in the batch scope, we have in the batch approach, the scope is fixed. We can't compose, in the sense that so, for example, imagine that we have a transaction with, 10 proofs. So the first prover could aggregate the first 5 proofs and then pass these ones on to the next prover, which might be a different controller, for example. And then this one would aggregate the other last 5 proofs of the transaction. We can also have a compatibility with composition in transactions. So that's something that might be useful in the future. The other aspect that is important, maybe it's not, but I think might is important at least to mention, is that the aggregation instance is the size of the aggregation instance for the batch approach is large. It's basically all the outputs and verifying keys that are present in the transaction. But for the sequential approach, this is very short. It's just a pair of hashes, and this might be important in the context of verifying proofs in smart contracts, for example. Yeah, because verification is always linear in the size of what is being verified. Okay, the most important metric, of course, always is the efficiency. Actually, the batch approach is the most efficient one. So here we can see that the batch approach it generates roughly like these are numbers for 6 aggregations. So it takes roughly like 1 million cycles to do 6 aggregations, and the sequential aggregation, a single step it takes much less. So if you multiply the number of cycles by 6, you will get less than the number of cycles in the batch approach. So it's in principle it's a little bit more efficient to represent. And regarding proofs, we have benchmarked two types of proofs: Starks and gross 16 proofs. For Stark's aggregation in the batch approach takes roughly 30 seconds, and proofs are roughly of 200 kilobytes. And for gross 16, it takes it takes like 50 seconds, but proofs are very short. And for the sequential, for the Stark approach, is almost the triple the proving time, the aggregation time, and for gross 16 is almost double. Okay. So now to conclude, I'd like to go through next steps that we could look into it in the future. So the first one is doing PCD-based aggregation. So this is kind of generalizing the sequential approach. Remember that this is in the sequential approach, we do one aggregation at a time. This is an example of what is called proof carrying data computation, where the idea is to split large computation between different nodes that do not trust each other. Each node, besides computing its own chunk of the program, it also attaches a proof to it. So this is exactly what IBC does, but IBC does it in a sequential way. There is no reason that we have to stick to sequential aggregation. We can change the shape of the transcript. For example, we can use binary tree transcripts and aggregate in layers. In each layer, we can prove things in parallel, so that might already improve efficiency. That's one of the advantages. Also, when we are talking about proving things in parallel, we can prove them in different machines, which is something we can't do with the batch approach. The PCD binary tree transcript that is depicted here is better than if we use if we put all the transaction proofs in as leaves of a tree and then aggregate them, because that would require like twice number of nodes for aggregation. So the aggregation overhead would be shorter in this case. And the question is whether this matches or improves the batch strategy. So this is the first thing that we could look into it, PCD-based aggregation. The other thing is, what about using an accelerator? So the observation is that aggregation is a very specific task. It's basically the CKVM verifier plus some optional hashing in the PCD-based approach. So we are currently proving computational iterations for aggregation in RISC-0, and the error in RISC-0 targets RISC-V traces. So these basically are errors with many columns in it because we have to describe all the opcodes in RISC-V. Even though it's reduced, there are many opcodes. The question is, if we use a custom R for aggregation, we might be able to get less columns in there, so would speed things up. Maybe we can use the low-level language that RISC-0 provides. This is very low level. I don't think it's very well developed, but might be worth to look at it. It's called Surgeon. Yeah. So accelerators for aggregation might help here. The last thing is more maybe on the theory abstract side, is whether function privacy, whether we can achieve function privacy using aggregation. So if we are able to move the logic verifying keys to the witness to the inputs of the programs, then we might get two things at the same time. So we get short proofs, a single proof for the entire transaction, and as well, this proof wouldn't leak what logic verifying keys were present in the transaction in the first place. So yeah, function privacy might be a good thing to look at. Yeah, this is it. Thanks for listening. Hope I didn't go too quick. If you have any questions, please do. There is a GitHub pull request, and the approach for PCT is described in the forums. Thank you.